So, having discussed the conventional superconductivity thus far with some details, let us resort to the, or rather take a course of the discussion towards the unconventional superconductivity, and we will explain what we mean by unconventional superconductivity. So, the topic is unconventional superconductivity. But in order to do that, let us look at the some of the features of the conventional superconductors, which differ from the unconventional superconductors, and we will see that how they differ and how much they differ by. So, the features are that the Cooper pairs form with opposite spins and momentum. Just to remind you that the Cooper pairs have momentum k and minus k, and the spins are up and down, and these are the constituents of the Cooper pair, and they form via electron-electron interaction mediated by phonons. A very important point which is not explicitly stated is that the angular momentum of the pair, that is the net angular momentum of the pair as well as the condensate superconducting condensate is 0. The Tc, the transition temperature that we actually see for these superconductor, that is the temperature at which the system makes a transition from a normal metal to a superconductor. It is of the order of, so Tc is small, and in most cases Tc is less than equal to about 25 Kelvin. So, that is the maximum Tc that one can get for these conventional superconductors. The magnitude of the gap is rather small. It is 1 to 2 millielectron volt, or it could be 3 or 4 millielectron volt, but it is of the order of a few millielectron volts, and so this is called as the delta, and this quantity 2 delta 0 over KTc, it is a number which is like 3.52. Usually it varies from 3 to 4.5, and these are the and delta 0 is the magnitude of the gap at 0 temperature. So, how do we now recognize that the unconventional superconductors, how do they differ from these conventional superconductors? So, in order to understand that, there are some empirical data that were first plotted by Uemura, and they are presented in the name Uemura plot. So, what happens is that the Tc versus Tf, so this is Tf in Kelvin and this is Tc in Kelvin again. They are plotted in the log-log scale. So, it is a log-log plot. So, it is actually a log Tc log Tf plot, and so this is like 10 to the power 1, this is 10 to the power 2, 10 to the power 3, and 10 to the power 4, and 10 to the power 5, and these are again so 1, 10 and 100 and so on. So, Uemura found that for the unconventional superconductors, they fall in a reasonably a straight line in this log-log plot. So, this is where the organic superconductors lie, and here are the so called high temperature superconductors, and we will include a discussion on them. And this is where the conventional superconductors. So, these are the conventional superconductors. In short writing SC, and these are the straight line that is drawn is where the unconventional superconductors lie. So, in the log Tc versus log Tf, Tf being the Fermi temperature. So, they lie on the straight line where these initial portion is occupied by some of the organic superconductors, and the later ones are occupied by the high Tc superconductors. So, this is called as a Uemura plot, and the conventional superconductors stay far away from this straight line. So, if you take this, I mean of course, there are sort of it is not along a line, it is just in a region which is far away from this straight line. So, if you take this as a marker for the unconventional superconductors from those from the conventional ones, then of course, we know that. So, this is an empirical plot, and so what happens in this unconventional superconductors? Do we still have Cooper pairs? We have to have Cooper pairs, right, because the Cooper pairs are the most important ingredients for an energy gap in the excitation spectrum, and that makes the superconductivity stable. Even if the gap is of the order of a few milli-electron volt, it still gives rise to a transition temperature to the tune of 10 to 15 Kelvin. So, if it involves formation of Cooper pairs, as the unconventional superconductors still have Cooper pairs as their the most important elements or constituents. So, there is a 2e charge that needs to be seen, and this 2e charge, as we have seen earlier, that the 2e charge is confirmed from the flux quantization measurement, and the value that we get is around 2 into 10 to the power minus 15 Tesla meter square. Is a small value, but it still confirms that one needs a 2e charge in order to get the flux quantum to be having this value, which are verified in experiment. Now, we need to understand that how the spins are opposite equal, I mean that is the formation of Cooper pairs is facilitated by the pairing of an up and down spin electron. That can be done or understood by the night shift measurement. And so, what is a night shift measurement? Let me describe this. In ordinary metals, the electrons, the magnetic moment, effective magnetic moment of the electrons, they are really, the net magnetic moment is really small, and it gives no contribution to the precision of the atomic nuclei. But however, if you put them in an external magnetic field, the electron spins will tend to align in the direction of the field due to Zeeman coupling. And because of this, the atomic nuclei now will be in a much greater field and will start precessing about that that magnetic field with a frequency which is known as Larmor frequency. Now, what happens is that if in a superconducting specimen these conduction electrons are minimal or they are almost absent, then this precessional frequency of the atomic nuclei or the nuclear the spins, these frequency will go down drastically, and this shift in the frequency as we go deeper into the superconducting specimen is called as a night shift. So, a night shift measurement is usually like this. So, this is plotted as a function of T over T c, and it falls off like this very quickly beyond. So, this is T by T c equal to 1. So, this is the superconducting part of the sample, and this is the normal phase of the sample. So, as the number of conduction electrons go down drastically, this night shift also goes down drastically as we are deeper into the superconducting specimen. So, this again gives rise to the fact that the Cooper pairs are indeed formed of charge 2e, that is there are 2 electrons involved, along with the fact that they have the total angular momentum equal to 0. Now, we are going to talk about angular momentum having different values, and that could be one way to give rise to unconventional superconductivity. So, let us just write this thing that Cooper pairs charge 2e spins up and down, which is encoded into this discussion. So, in the conventional superconductors, this is the free Fermi C, and this is what the so sort of if we write it in a kx ky in a 2-dimensional momentum vector or wave vector space, this is basically the filled Fermi C. So, this is the gap that we call as delta, which is of course a function of temperature, but we are just denoting it at a given temperature. So, this gap is isotropic in a conventional superconductor. Okay, which means that the delta has no k dependence. Okay. And this was also clear when we actually derived the BCS equations, in which the gap equation took a form that there is a sum over k prime and a v k k prime with a delta k prime and a 2 e k prime, and then of course, we can have a tan hyperbolic beta e k prime by 2. Now, this if we take an approximation that v k k prime equal to minus v 0 for psi k and psi k prime to be both within an energy range which is h cross omega d, then of course, then this equation tells you that if you put v k k prime equal to minus v 0, it tells that delta k is independent of k. And we have an isotropic gap. That is, does not matter which way you try to, or which part of the Fermi surface you try to excite an electron, to overcome the gap you have to supply the same amount of energy. So, this is the story with the conventional superconductor. Now, the question is that If that does not happen for the unconventional superconductor, then let us see or let us assess, evaluate the scenario. Now, it could happen the unconventional features could actually get generated from a variety of factors, but at this point we are considering that this is one of the reasons that unconventional superconductivity can arise. So, let us talk about finite momentum pairing. In other words, the two electrons come and they collide to form a pair, and which is mediated by this pairing is mediated by phonons. In this particular case, the vertex actually contributes to the momentum, either it carries momentum away from this collision or it imparts momentum to the collision. So, a finite momentum pairing, we can think of that the angular momentum of the pair can be a one even multiple of H cross and two odd multiple of H cross. This odd multiple of H cross involves what are called as triplet pairings or p wave pairings and so on, which will shelf for the time being and only talk about even multiple of 2H or even multiple of H cross. So, which is the lowest value is 2H cross, and that is called as the. So, this even multiple of H cross is called as the singlet pairing, and the odd multiple is called as the triplet pairing. So, we are just going to talk about the singlet pairing. And we will talk about an angular momentum equal to 2 H cross, and so this is called as the D wave pairing. This is true in the context of, at least is believed to be true in the context of the high TC superconductors, that many of the high TC superconductors they have a D wave pairing. Now, in order to understand what D wave pairing is, let us see that your, so this is in units of H cross. So, we will just take that unit out. So, L equal to 2, that is the angular momentum quantum number. So, basically the capital L has got 2 H cross. So, L equal to 2 means ML equal to -2, -1, 0, 1, 2. So, these are magnetic quantum number values. So, these so there will be terms such as 2 -2 to -1 2 0 and 2 1 and 2 2. So, these are the possible D wave pairing, and they have names. We are not writing them particularly in order, but they are written as D X Y pairing and D Y Z pairing and D ZX pairing, and then or it is also called XZ pairing, and the D X square minus Y square and D 3Z square minus R square. So, let us only discuss one candidate and see that how this particular symmetry, each of these symmetries they look like, and we will just take a look at this D x square minus y square pairing. And for illustration, let us take a function, take dx square y square in the xy plane. Okay. And we will write this f of x y as x square minus y square on a unit circle x square plus y square equal to r square equal to 1. So, which means that y square is equal to 1 minus x square. If we substitute in f x y, this will be like 2 x square minus 1. And so, this 2 x square minus 1 is the function. So, you see that this function is maximum or rather it is minimum and has a value which is when x equal to 0, that is on y axis, and it has assumes a value minus 1, right. When x is equal to 0, it is equal to minus 1. So, this is 1 and 2, it is maximum for x equal to 1. So, maximum when x equal to 1, that is of course on the x axis and assumes a value plus 1. So, that is the nature of this, and so basically it changes sign somewhere going from y axis to the x axis. Let us see what more we can learn from this. Third is simple, that for x square equal to half or x equal to plus minus 1 by root 2, basically f x changes sign. You saw that on the y axis it is minus 1, on the x axis it is equal to plus 1, and so it must be changing sign somewhere, and we want to see where it changes sign. It changes sign along the diagonal. So, at this locations we have mod of x equal to mod of y. Okay. So, so the sign change along the diagonals. There are of course, 2 diagonals there. So, what does the function look like? The function looks like this, it is called as a clover leaf, and it has a form which is okay. So, this is equal to minus, so this is y axis, this is x axis, this is plus, this is minus again, and this is plus, and this looks like a clover leaf. So, this is the form of this dx square minus y square symmetry, and we can also characterize this f x y in terms of polar angle. Theta, I mean f of theta can be written as sine square theta minus cosine square theta, which is minus cosine of 2 theta, and if you plot it it looks like -1 and then it goes down and then it goes up and then it goes down and so on. So, this is where it goes down once more. So, this is 0 and this is 2 pi, this is pi by 4 where it is 0, this is 3 pi by 4, this is 5 pi by 4 and this is 7 pi by 4, and these are the positions which are pi by 2 and 3 pi by 2 and 5 pi by 2 and so on. So, this is I am sorry. So, this is pi by 2 and so this is actually 3 pi by 2. And so on. Anyway, so that is the form for this d wave order parameter. Now, what is it good at and how are we going to connect it to the superconducting order parameter? Now, if you have if you consider the same picture as we have considered earlier, that is that there is a Fermi sphere or the field Fermi C, which is like this, and we break it into quadrants and so on, and then we draw diagonals. Let us draw the diagonals with a different color. So, these are the diagonals and we could draw it with another color. So, these are the gap functions. Now, the gap has a k dependence, it is not isotropic along all directions, and we have. So, this is called as the d wave gap. Okay. And so, what it means is that there are points which are along the diagonals. These along the diagonals there are points which are 0 gap or they are the gapless superconductors. So, along this direction there is no gap in the single particle excitation spectrum, and the electrons can actually be excited without imparting any extra energy. And if this is truly the structure or the geometry of a gap function, which has of course a k dependence. Now, we are drawing it as a function of a k x and a k y. Then these should be some experiment should be able to see these gaps, and let us call these points as A, B, C, D, which are these points where which are called the gapless points, and this A, B, C, D are also called as nodal points. Or they are also called as the gapless points. So, if this is the structure of the order parameter in an unconventional superconductor, in the conventional superconductor of course, we have seen that the gap is isotropic in any direction, but suppose the gap has such a symmetry, then what are the things that we expect. And of course, as you can see that the other dxz, dyz and xy etcetera, d 3z square minus r square is more complicated. These other things have gaps around different directions, and but by and large this explains that how is the dx square minus y square, that gap looks like. So, it has a k dependence. So, the gap has a k dependence, which means that the wave function, that the Cooper pair wave function pair has a form which is psi equal to psi 0 k x k y and exponential I theta, where theta is a phase factor and the energy gap has also a structure. This is delta equal to delta 0 k x k y and exponential I theta. And of course, what we understand by this picture is that, so this phase factor of course indicates the motion of the center of mass of the Cooper pairs along a specific direction, along a particular direction, and the mod psi square gives the density of Cooper pairs in K space. So, since along this diagonal the density vanishes, which means at the nodal points A, B, C, D, the density of Cooper pairs is equal to 0. And additionally, one can say that there could be gapless excitations at those nodal points. And of course, one understands that psi 0 is proportional to delta 0. So, one actually gives a measure of another. So, even if we talk about just one quantity, that is going to be enough. And let us now see that a possible experiment that can determine a gap structure of this kind, and that is called as the angular resolved photoemission spectroscopy. And in short, it is called RPES. Let us draw this, one can. So, this is the surface of a superconductor, and there is a photon that comes. There is, let us draw the coordinate axis here. So, there is an electron that is emitted in this direction. So, this is a h nu, which is characterized by a vector potential A, and this is in a detector. So, this is a detector, and the electron is actually captured by the detector. So, this angle is called phi and this angle is called theta, and so this is the y axis, this is a right handed coordinate system, and this is the z axis. So, the photon falls on a certain material which is a superconductor, and then electrons are emitted and they are collected by the detector. So, it is very clear that if you have electrons available in certain directions, then only the detector will be able to detect electrons, and this detector can be actually placed at any angle in a 360 degree, or rather full covering the full angle. It can be placed at any angle. So, this detector only detects electrons at say 4 location or at the 4 points in the kx ky direction, in which the system has or the superconductor has gapless points. And if we can do that, then only we see that the electronic density of states which is obtained from a peak in the single particle density of states. So, it basically scans or rather detects the single particle electronic states. So, this signal is Fourier transformed to K space to obtain K versus E plot, which is nothing but the density of states, where the photo emission intensity is given by, I am going to write some equations which are really required, but just understanding the physical context of doing this experiment is good enough. So, what I mean to say is that this detector only detects electrons in certain directions when it is Fourier transformed into the k space, and those directions are the gapless points or the nodal point from which electrons can be emitted with absolutely without any difficulty, because the other places there is a superconducting gap and the electrons cannot come out, because that is the energy barrier that has been created by the formation of the Cooper pairs. So, the photo emission intensity is given by W f I, which is equal to 2 pi over h cross and a psi f h prime psi I mod square delta of E f minus E I minus h nu, that is the energy conservation. And what is the, so one has to do a second order perturbation theory in h prime in order to get the intensity. This is called as the Fermi's golden rule. This you might be knowing from your course of quantum mechanics on perturbation theory or scattering theory. And this h prime is nothing but the E by 2 m and the A dot P plus a P dot A, that is the coupling between the vector potential and the momentum of the electron. And by a suitable choice of gauge, one can show that these two with the gauges that delta, that is divergence of A equal to 0. In this gauge, this E over m, it becomes E over m A dot P, that is both the terms become equal and they add up in order to give a factor of 2 which cancels with this 2. For a given gauge, I simply write it as this, and this can be shown. Now, h nu, which is the energy of the photons, and A are basically for a given radiation are fixed during experiments. The kinetic energy of the electron E k, then work function, which you must be knowing from Einstein's photoelectric effect, that there is a certain amount of work function which is associated with a particular material, which is a property of the material, which is called work function, that has to be overcome in order for the electron to emit, and the polar angles theta phi are measured. Okay. So, what are the conservation laws? The conservation laws for this photoelectric or rather this angular resolved photo emission spectroscopy are simple, that is the kinetic energy of the electrons, which is equal to h nu, which is the energy of the photon, minus the work function minus the binding energy of the electrons in a material, and the parallel component that is conserved and this is equal to 2 m E k and a sin theta. So, now the only constraint is that the ejected electron or the emitted electron rather this assumption should be fast enough to be able to neglect the interaction with the hole left behind. So, RPES finally gives direct information the electronic states. Okay. So, that is the way that one can actually understand that the gap function of this Cooper pairs that has a structure and is not uniform in K space. It has some nodal points from which electrons can be excited, and that can be detected via an angular resolved spectroscopy, photo emission spectroscopy, and this has indeed confirmed the presence of a D wave gap in certain unconventional superconductors.